Hello everybody. But as it seems that in my previous attempt to do a nice podcast for numerical geometry, I made a small mistake with the sound, so I will do it again. But basically, as I explained before, I will give you some few information, few words about quick. That is a wonderful algorithm to compute a convexe. It's not the best one, but it's a funny one. Basically, it looks like that. So you have some node like that. Below, 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 like that. That's plenty of node. You select the top, highest, the top. You select the lowest. I will put here. Voila, like that. The lowest. Here. Okay. You select the most wide and the most left. And as a first attempt of a convex hull, you will define this shape like that, 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 and that. And you can eliminate all nodes that lie on the left side of the four segment, but you have still some remaining node like this one, this one, this one, this one, and this one. The idea is when you have a straight line, you compute, you'd find the node that is the most maximum distance from the line, and you do it again by drawing a line like that and drawing a line like that. Okay, where I will move a little the drawing to see better, like that. Okay, you see it. And now you have only one remaining value here, and you obtain for each side. It's a recursive approach. It's called the quick hull. It's a little like the quick sort. Okay? So basically the algorithm is the following. So now I hope that if I remove the webcam, you still listen me like that, and it works. Yeah. So basically it's a recursive procedure. So it means that you have a function q that will provide the node that are located on the right side of an edge defined by vi, vg. And you have a lot of s. So what are you doing? You are doing that you compute if the set of remaining vertices is not empty, you compute the position of this vertex that I will call V, and you do the same job for the point y to vi, v, and for v to vj, and you concatenate the result. And in such a way, you will obtain finally the convexe. So the idea is that you have a large number of points, you divide the job in two subparts, and you apply a recursive algorithm. It's a nice algorithm, it's not difficult to implement, and it looks really funny. So now I want to analyze, to do the complexity analysis of this stuff. And the idea is the following. I have y, q, s. S, you assume that the dimension of S is n, and this cost is obtained as the merging cost of both data from I and data from G. This stuff, I will call it T of n. Okay? And basically, this is the two sub-problem, and now I can try to imagine what can happen. You can be very, very, very lucky and imagine that you have two nodes like that. You have a straight line like this, and you find the most distant node like this. You draw two curves, two lines like this, and all nodes are inside A. That is so fun, but it's like winning to the bingo. It never happened, so I don't consider this case. What I will call, in fact, the best case is not so good. The best case is something that is not so good, is something like that, is pilu pilu. It is something like that. That is the best case. Is that the dimension of I is n divided by 2, and dimension of G is n divided by 2. Basically, you are not very lucky, but not a totally bad situation. So it means that you have the blue curve like that, you have a node here, you have a curve like this and a curve like this, you have 3 dots here, 3 dots here, and you obtain that basically you reduce the size, you eliminate no node except one, but the two numbers are better. That means that you have basically T de n is order n plus 2 times the cost of an half problem. And this is typically a divide and conquer recurrence. And divide and conquer recurrence. You have a problem and you divide the problem in two smaller problems. And if the merging cost is linear, you are pretty sure that the global complexity of this stuff is O the n log n. But that sounds not so funny, but in fact is the good case. The worst case is the following. The worst case is that. That is the worst case. Dimension of I is 1. Dimension of G is n minus 1. It means that you have a segment like that, a curve like that, a node like that, and all stuff is A. that is very, very bad. Because if this happens each time, you will have that Tn is basically O the n plus n minus 1 plus n minus 2 plus dot dot dot, and that is basically bar, because now you have a cost of n square, and that is not very exciting, not exciting at all. So basically, as a summary, you have that. You have the best case, it's not really the best case. The worst case, that is really, really bad. Obviously, you will tell me that you must be very, very unlucky to fail at each time. But it can happen. Okay. Now, how to estimate the divide and conquer recurrence? Basically, the idea is to write that T of n can be written as a merging cost that is proportional to n and 2 times the subproblem. You see that? You assume without generality, without losing any generality, that n can be viewed as 2 at the power k. And if you write that, you can develop step by step and observe that finally you obtain n log n. You will tell me, yes, but if n is 62, but just assume that it's bigger, equal to 64. It's easy. Okay, and now a few words about upper bound and lower bound. It's a formal definition of the upper bound. It's a set of functions. When I write big O is a set of functions such that for a given value of n bigger than n0, it exists a constant such that g to x. Basically, it means that if you do a graph like that, if you say that is O of n squared, it means that you can write a curve like that, c n squared, and that your function, starting from a given n0, will always below this curve. And now you can write also omega, for example, of n. And it means that this curve is always above this curve, omega. And that is a lower bound. It means that it's impossible to have an algorithm that is faster. And typically, we will prove that the Hull construction cannot be performed faster than with an n log n algorithm. Of course, the constant might be improved, but you will never obtain a linear algorithm. That is impossible. This must hold for any possible algorithm. And that is quite difficult, because to imagine that you have it for each algorithm means that you have to imagine all possible algorithms and check it for all possible algorithms, and even the algorithm that people will create in the future. So imagine that you are very, very smart and you think, I will create a new algorithm to do that. And even this new algorithm will not be in order n. It will be order n log n. The constant before might be smaller, but it will not be faster. That's your view. Okay? So the idea to demonstrate it is the following. You take a problem that is well known, for example, sorting a set of numbers. And for this problem, it's well known, it has been demonstrated long time ago, and I assume that it has been known, that is proven, that is written in book, typically a book from Knut. It's a well-known, an old book, well known, that proves that it's impossible to do a sorting algorithm faster than n log n. Typically a quick sort. Okay? And now you will demonstrate that because it is impossible to sort number in a faster way than n log n, it's the same for the convex construction. Why? It's pretty easy. You will reduce this sorting problem to the new problem. And it's very, very non-intuitive. It's very non-intuitive. You take a problem, you take a known problem, the sorting problem, and you will reduce this known problem to the problem you want to analyze. And you will consider problem B. So you reduce the known problem sorting in the new problem, problem B, and you will assume that you find an order n algorithm. And if you have an order n algorithm for building a convex hull, now you apply this convex hull algorithm to the following set of nodes. The value v that is defined like xi and xi square. Okay? And if you do that, you will obtain, in fact, the convex hull described on the figure. This part here, you. And if you are able to build the convex hull in order n algorithm, you do in the same way the sorting of the data. So you solve too quickly the sorting algorithm. And this is in contradiction with the fact that you know that it's impossible to solve a problem in order n. And if you obtain that, you prove that it's impossible to build a convex hull algorithm faster than n log n. And it's a very standard approach in the field of complexity analysis. When you know that a problem cannot be solved in a faster way than n log n, and you can reduce this known problem to a new unknown application, you can use the fact that you know that the first problem cannot solve in a faster way than n log n. That is very, very clever. And so that is the end of my small podcast for numerical geometry with the song. Sorry for the inconvenience. I will try to do better next time. So that's the life. Okay, and now I am back. If 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 I am here, you listen me. So I have still to do some small improvement to have a perfect stuff. But now I start to manage a little the technology. I want to do some very sophisticated stuff. It will be better. So that is the end of a podcast. Next week better podcast, better stuff. Be cool. It will come. Don't be worried.